This nugget has one mission and one mission alone: to show how spoken voice becomes a packet, or more specifically, the analog to digital conversion process. Now, for those of you that are solely real-world people, like I am just going through this series right now because I am doing this, and this is what my company needs, then I would say shuffle this one to the end of the stack. The reason I say that is this is, if you go through this, I guarantee you'll be like, oh, that's how it works. But really, this is certification minded. For those people that are taking the certification exam, you'll want to know the terms that I'm going to talk about. You'll want to know the process. And it's have you ever gone to that website howstuffworks.com? It's one of those addictive places where it's like, how does a microwave make my coffee warm again? And you okay, so it's one of those kind of things. Like, this could be a submission for howstuffworks.com. However, is it absolutely necessary to know this to implement it? No, definitely not. It's just you're going to see these terms all over the place. That's why I decided to break this topic into its own nugget, is so that way you could make the choice whether you want to get the information for certification, or if real world's gonna move it to the end. So here is how spoken voice becomes a packet. And let me expound a little on these points that you can see right on the screen. First off, we have an analog signal. That's what we start with. And what is analog? It's using the properties of something to represent audio. So in most cases, we're using the properties of electricity. We're saying, okay, I want to see the amplitude of how high this goes, which represents the strength of the voice, and the interval that this repeats itself, which is really getting into the frequency of it. And that's how we're able to put together and generate an analog signal. But the problem with analog and using electricity is that as you go over that wire further and further and further and further, it fades away. So you have to put a little regenerator in there that blast it back up, and then it fades away. But every time you regenerate it, it gets really strong and increases all the background noise. So you get hiss on the line and all that. So analog just doesn't go further. Enter into the picture our hero, Dr. Harry Nyquist. Dr. Nyquist, long ago, was the one who forged converting analog signals into digitized format, the way that we know it is into binary, into zeros and one. And the way that he did it is come up with the theorem. And yet if you talk to any PBX person and say the Nyquist theorem, it's like, it's like what was that, Wayne's World? Back in the day with Wayne and Garth, they're like, oh, we're not worthy. It's like everybody knows the Nyquist theorem from the PBX world. And what it is, and let me see if I can paraphrase it as simple as I can. He said, when you have a sound, if you can sample that sound as much as the highest frequencies, hang on, I said as much, no. If you can sample that sound twice as much as the highest frequency, you can accurately regenerate it in a digital format. Now, if it's your first time hearing that, or maybe even if it's not, you probably hear that and go, huh? What? What do you say? And trust me, that's totally fine. I would be baffled if I heard myself say that the first time too. What he's saying is, when you look at human voice has a frequency range, and this is debatable. You'll see it all over the place, but frequency range of about 20 to about 9,000 hertz. We have a really low signal and really high signal, go all over the place with the frequency. But the core of human voice, meaning the meat of it, if you can. You've got kind of the highs and the really lows, but the meat of human voice is really at that 20 to 4,000 hertz range. So what Harry Nyquist came out and said was, okay, if we take the core of human voice, 20 to 4,000 hertz, and we sample it twice as much as the highest frequency. So what's 2 times as much as 4,000? 8,000, right? So we sample it 8,000 times. What do you mean 8,000 times? 8,000 times a second. We can accurately regenerate human voice. Okay. So first off, there's a little conversation around that I want to have with you. When you're talking on the phone, it doesn't sound as good as like THX surround sound, right? I mean, it's like when you're listening to AM radio, talk show, you're hearing about politics or something, and I think that, such and such, let's take some telephone callers, and you get the telephone callers on there. He's like, well, I think it's totally wrong. And I mean, you don't freak out because you know the telephone caller doesn't sound as good as the radio host because AM has more frequency spectrum than a telephone does. You just get used to the way that people sound on the telephone, and that's because we're not getting the full fidelity of their voice. We're just going for the meat. And Nyquist's goal was that you could recognize the person, like when you call or someone calls you and you're like, hey Bob, you recognize them by their voice, and you can tell their mood. You don't want to take it down so far that you get the audio but you can't tell, they're like a robot and I cannot tell what kind of, you could sample it that low, but that's not what we want. So that's what this frequency spectrum comes in. Okay. So that's why he chose that, which is the meat. I'm going to call it the meat of human voice. So now what's with the 8,000? 8,000 what? Well, that's where we come into this scale called PCM. What is that? Pulse code modulation. What is it? It's a sampling scale that converts this into a bunch of binary numbers. Matter of fact, 8,000 of them every single second. So here's 1 second of audio. So let's say, that was my theme in the last nugget, right? I say the word cow. It's kind of going across that 1 second of audio, right? So what PCM does is it says, okay, I'm going to sample this spectrum with little 8-bit samples that, let's see, what's the best way to put it? That go in a positive, negative place. Now, okay, 8 bits, right? Remember your TCP/IP subnetting from CCNA? How many values do you get with 8 bits? 256. Well, if you think about it, 0 through 255. So what PCM does is say, okay, well, our frequencies here go up and down, they're positive and negative. So what I'm going to do is I'm going to take the bits and I'm going to have, the first bit, on the far left will be my positive negative analyzer. And then the next 7 bits are going to represent what number this is. And you can get deep into this. You can say, oh, okay, well, this is broken into 2 sets. One's the sequence. I mean, yeah, don't even worry about that for now. It's going to figure out what number this is. So 8,000 times a second, it's going to say, okay, I've got, let's go simple. 1, 5, 6. Now we're up to 22. So it's actually sampling this 8,000 times a second. So there's my cow, all the way through. Now, one of the things that PCM does is it samples more down here. It's a non-linear scale. Meaning these higher frequencies up here don't really contain as much of the meat of human voice as these lower ones. So to accurately get that voice it's got 256 numbers, 0. So it goes 127 up and 127 down on that scale. So what it does is it puts a lot more samples down here really close. I probably didn't do this as accurate as I could. Down here really close, and then as it gets further up on that range, starts spreading them out more and more and more and more. To where the samples get more spread out, thus not as accurate for the higher frequencies. That's why if you pick up the phone and you're like, ah, you just start screaming at somebody. You're way down here. The phone's crackling, breaking up. It's like not only are you overdriving the handset, but PCM you're way down here in the scale. It's like trying to regenerate it. It can't do it. It's too well. It can, but it's just choppy because you're way outside of the normal human voice frequency spectrum. So it's not going to be as accurate. Does that make sense? All right. So I'm talking about all these little pieces. Let's put it together. Meet human voice, 4,000 hertz. PCM is the scale that we are sampling that 4,000 hertz. So here's our 4,000 hertz, if you will, of spectrum that we're sampling on there, and we're sampling it because of Nyquist's theorem. We're sampling it 8,000 times a second with 8-bit samples for each one of those. So, I've got a positive, 2, 3, 4, 5, going all the way up here. So you get all those. So we take this and we kind of put it together. We go, okay, 8,000 samples, 8 bits a sample. Okay, carry the 1, 64,000. Wait a second. That's a familiar number. Bits per second. That, my friend, is where we get that 64 kilobits per second per audio channel. That's the kind of bandwidth we need to accurately reconstruct the human voice. Now, there are systems out there, for instance, your analog phone at home, where you don't get 64K because they have to have signaling in there. So it might reduce the meat of your voice down. Maybe it goes to like 3,400 hertz that it samples, which again doesn't sacrifice too much unless you start getting those really high spectrums of or frequency ranges on there. So that's the process. I think I went through my numbers a little all at once. So sample the analog signal a lot. Create a number that represents each sample. That's known as quantization. Convert that number into binary, and that's where PCM kicks in, and it says, okay, here's the scale. So by the way, we don't just go, it doesn't say, okay, this is the number. There's a quantization scale which says, okay, this electric frequency, blah, 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 so there's a different scale. So PCM is what takes that electrical frequency scale and puts it into a binary number scale. Wanted to mention that as well. And then you now have the audio. This is how we get G.711. Now we come to this mu law or A law. You might remember in the previous nugget when I was talking about that, there are two flavors of G711. Most people write it U law, and most other people write it A law. The U or the mu is a Greek something or another. It's Latin, or I just throw languages out there. It's Spanish or French. I think it's Latin. That says, okay, this is the United States of America. That's where I got that from. But it has one kind of PCM scale that it uses, which is actually backwards from A law. A law is a lot easier to talk about because it just makes sense. So if I'm doing A law, the way the scale works is I say, okay, if it's positive, this will be a 1. If it's negative, this will be a 0. And then these digits represent, essentially 0 through 127. So if I was doing, for instance, the number 64, it would say 1 1 0 0 0 0 0. 1 meaning it's a positive on this scale, and then right there is the value of 64. I think I may have dropped the 0 off. 1 2 3 4 5 6 7. Yeah. So it's a value of 64, right? So that's A law, the it makes sense coding. U law is the same thing but backwards, to where if you're using G711 U law, the way it codes it is it says 1 for a positive number, but then 0 1 1 1 1 1 1 1. That's 8 digits, right? Is 64. Huh? Yep. They just decided, with U law, let's go backwards from whatever A law is. So what that means is if we have a phone on one end of the world speaking U law in the United States, talking to another phone on the other end of the world speaking A law, we have to transcode those, which is essentially the transcoder has an easy job. It just takes these coming in and, it says, okay, that's the U law version. I'm converting it to A law, which looks like that. They're just backwards from each other. And it makes me wonder. I'm sure there's a technical reason why they did it that way, but for some reason my mind just goes to, all the politics where some guy in some country is like, I don't like your coding method, I will make my own, and it will be backwards from whatever you do. So I don't know why we ended up with the two formats. Maybe, that would be a fun homework assignment if you are wanting to go to howstuffworks.com or something like that. But that's the two different coding methods that are out there. The final piece in this process is to compress it. If desired, compress it. So these three is the process of converting spoken audio, an audio waveform, into digital format. Numbers that can be transmitted any number of distance, any amount of distance, without losing their signal. The last piece, if you want to, is to compress it. That's where G729 or ILBC or all the other compressed codecs come in, is they take it and now run that through a processor, which makes it more efficient. Now, one more piece to put into place. Remember I said, if you remember on the last nugget, is that right, where I was talking about the codecs? Is that the last one? I think so. G711 by default uses a 20 millisecond sampling, and that generates a packet payload of 160 bytes. If you think about it, and this is the fact, G711, every single packet contains 160 individual numbers, individual samples. So, when I'm saying the word cow, it's going going up this scale or whatever the case is. Now obviously I can't draw 8,000 lines in this 1 second interval, but that's really what it's doing. Is it's taking 160 numbers and sending them over. So if you lose a packet, in reality you're losing 160 values that it sampled, which sounds like, wow, that must be impactful. But when you think about it, it's taking 8,000 of them a second. Maybe it's not. Chances are pretty good all those numbers are almost, if not all, the same. Isn't that neat? I mean, if it's your first time seeing something like that, I know when I saw it for the first time, I was like, wow, that's pretty cool. So what did we see, and then what do I want you to do with this? We saw the process to convert from analog to digital, a process Dr. Harry Nyquist discovered, I believe it was back in the 60s, is when he was putting those together. Might have even been the 40s. Again, Wikipedia tells all, right? Just search for Dr. Harry Nyquist. But that process introduced a lot of key terms, things like quantization, things like PCM scale. These are things that you will see constantly in the voice over IP world, in debug messages and processes and reading textbooks about it. So now you'll be able to fit those together. So what do I want you to do with this? Well, of course, dwell on it for a little while, think it through, but then go tell a friend. I mean, explain it to a friend and just kind of draw it up, because it'll be the best way to know that you actually understand it. And your friend at the end of it should be like, wow. I mean, of course, spin it so it sounds more interesting than let me tell you the process of quantization. I mean, just be like, hey, I noticed you have an iPhone there. Did you know that it's a springboard for any number of communications? Well, I hope this has been informative for you, and I'd like to thank you for viewing.